Okay, hello everyone. We're going to pick up where we left off on the in-class lecture. We left off here on slide 18 of the slide deck, U-value of insulated glass. As discussed, the U-value is kind of an indicator of how good the glass is at preventing transfer of heat from one side to the other, okay, as measured in BTUs as we look forward in the U-value problem that's in the slide following this. But basically, if you look at the U-values, again, they're the reciprocal of the R value. The smaller the number, the better the insulator, so the harder it is for heat to transfer from one side of the glass to the other or escape from one side of the glass to the other. So as you can see, based on the different half-inch, the different thicknesses of the glass, glazing and thickness combined help give you a better U value. Right? But when you look at the comparison between number 3 and 4, double glazed glass versus triple glazed glass that's much thinner, it's the triple glazed glass that actually has the better insulating capabilities and the ability to prevent heat transfer. So glazing has a higher effect than the thickness of the glass, but both do contribute to helping insulate it. So it makes sense, right? A thicker barrier with more layers of protection will always be a better insulator than the thinner barrier with less layers of glazing protection. Okay. So we use that information on the next slide, which is our U-value problem where we left off. Okay. So we're talking about a small square foot area here, 10,000 square foot floor, meaning really it's only 100 feet on each side with vision glass. Okay, so we're talking, probably a curtain wall of some kind, and it's basically a glass-faced wall. We're not thinking any concrete cinder block type material, thinking glass all the way around. Okay, so we're looking for the BTU for the heat transmission through the glass with an indoor temperature of 75 degrees and an outdoor temperature of 95 degrees. And the assumption is we're using 1/4 inch double glazed and comparing that to 3/4 inch double glazed units. Okay. So the formula we need to use here and understand is that for temperature differences through a medium, whether it's glass, concrete, whatever, in this case it's glass, is the temperature difference between the outside and the inside times the surface area that this material occupies, okay, times the transmission coefficient U. And that will give you the BTU for the heat transmission that this difference in temperature causes through this glass material. Okay, so we'll take that and through the example here, temperature differential, or TD, is the temperature out minus temperature in. So here it's 20 degrees difference, right? We have 95 out, 75 in. So you're looking at it being pretty hot outside. You're trying to keep a temperature of 75 in. And then we're going to figure out what surface area does this now act on. So we know we have 4 walls that are each 100 foot in length and 10 foot high. That's why we need to know the height. So each face is basically a 10-foot high by 100-foot long wall of glass. And we have 4 identically dimensioned sides of the building. So we just simply multiply by 4 for each side. Okay, and then we multiply that by the U value of the glass. And that U value was shown a couple slides prior to this. You simply look it up on that chart. 3/4 inch double glazed has a U value of 42. 1/4 inch double glaze has a U value of 0.59, and you multiply them out. So the first one, 20 degrees difference, times the 10-foot high, times 100-foot length, times 4 walls, times the coefficient of 0.42, and you can see on that glass we have the heat transmission of 33,600 BTU, and that's using the thicker double glazed glass. When we go to the 1/4 inch, which is thinner, we know that that's going to lead to more heat transmission between the two sides because it has a higher U value So you multiply that out, the same 20-degree difference times 10-foot high glass walls times 100-foot long, and there are 4 of those walls, times 0.59, which is a coefficient. And we can see, since the coefficient is higher, the BTU, or the heat transfer between the two sides, is higher also. So that's 47,200 BTU. So in essence, if you have the lower U value, okay, your HVAC system is now going to, or AC system is going to have to now account for that kind of heat transfer through. So the glass we choose, the thickness, the glazing, the coefficient that we get from it makes a big difference in how the temperature outside the building acts with the temperature inside of the building. So it makes it easier for that hot air to get in if we have a higher U value coefficient for the glass that we have. Okay. So we're going to go through a couple of things now. That's critical. That's pretty important for the homework, as well as to know for the exam. I'm going to cover about 10 to 12 slides here that are not super critical for the exam, but just wanted to go over to give you an idea of what's going on. Organizations for design regarding HVAC is typically ASHRAE, right? American Society of Heating, Refrigeration, and Air Conditioning. Okay, they have they're the organization that basically comes up with all the design criteria, who tests various materials, and it's basically writes the manuals on how to do this kind of work on the engineering side. They look at the codes, they look at trends, and they try to keep up with what's going on and all the new things that are in the field. When they're designing for various cities around the country, there are published historical data that we utilize that kind of gives us an idea of what we should be looking at. And just for an example here, we see how number one, the average temperatures that we kind of design for on the high end are about 91 if you look at New York, even though we can get a maximum of 100 or more on a very hot day here in New York City. We know that we have that diversity factor, right? That we don't have to design for the highest possible temperature, because it's rare that it ever gets to that all the worst case scenarios are very rare. So we can design to something lower. But again, in this particular chart, you can also see in that middle section how the temperature within a conduit that's exposed to some kind of direct sunlight, all right, also heats up well beyond the stated air temperature in the area. So it's just another example how the sun and radiation and heat build up in areas just like within a building. Okay, so even though the stated temperature is 91, it can feel much hotter inside, and you have to account for that in developing your HVAC system. And again, weather patterns, they go up, they go down. We're all under the impression that there is global warming, so maybe in a couple of years that design standard will start to trend upward. It'll be monitored, it'll be looked at, and we'll see how things go. All right, so again, not in great detail, but we're going to go quickly through a couple of slides that just give definitions for key components of air conditioning systems. Again, I'm not looking for anyone to be able to design a system and know how each of these works, but in general, there's a couple of ways to cool. Major systems in buildings in New York use chilled water, through a cooling tower that's based on the roof of the building. Other systems use condensed water, cool air through fans. Some of the lead type structures now use ice storage as a natural source of cool air that they then vent through the system. And then there are other ways of cooling as well. But typically, we're just going to go through a couple of slides. I'll give you an opportunity to read the definition. Okay. And again, we don't need to know these word for word. Right, just for your own knowledge, to show that we covered these items and the topics. But we do you'll see a couple of diagrams coming up to kind of show where they are, and I'll run you through them, how it works. Okay, so the compressors are really similar to pumps. And they're utilized when we have different kind of cooling systems to compress the air and push it through. Sorry about that. All right, so the cooling systems in the building are very similar to what we have in our own body. This goes back to our first lecture where we kind of made the comparisons between the human body and having all the different systems from feet being the foundation to curtain walls being our skin, and the bone structure being structural steel. So again, there has to be something that equalizes temperatures in a building to maintain that temperature, just like we have certain things that equalize temperature in our body to maintain a good temperature within. Right, so our skin could be, kind of rated almost like an R value or a U coefficient, right, of how it may keep warmth in, and it could help release warmth through pores, just like an HVAC system can control air coming in and out to change temperatures. All right, what we have here is a typical automobile cooling system. So anyone that's into cars knows the basic radiator, and really the early cars used to be water cooled, and then obviously as the technology progressed, they ended up with antifreeze and freon and other things that can be used to not only cool the engine, but to also allow for cool air to be put into the car through an AC unit. And many units are tied together where if you think of an old refrigerator or a window AC unit, right, there's always some kind of balance of the temperature. Whenever cold air is being put into something like a refrigerator, or cold air coming through an AC vent into a room, there's hot air being expelled somewhere to balance out that change in temperature, right? So the back coils of of an old refrigerator would get hot and give off heat while it's also cooling on the inside. An AC unit's the same thing. Cool air coming in, but it's releasing or relieving hot air out into the environment from those units. So there has to be some kind of balance of the temperature. Okay, and the idea with water, whether it's in automobiles or whether it's a home heating system, is basically the fact that cool water is continually pushed through. There could be a fan blowing, on the pipes that have that cool water, or other ingredient like a freon, making it cool so that it blows cool air out. But what that liquid is really doing is extracting warmth from that air that's being blown in, and then it's being taken back out through the exhaust side. Okay, and again, within an AC unit, it has again different types of refrigerants that could be used versus what was first cold water. We can use the same kind of idea on larger systems for air cooling within a home that aren't window units. And eventually you get to the larger units that are based on the roofs of buildings. Okay, so part of what we look at and our interest in knowing the numbers, not so much for just knowing numbers, but again, we size systems like this, AC systems, in terms of tons of cooling, right? And when we find out what we need in our building, we can then find out, the cut sheet from the manufacturer that tells me what this unit is, how much electrical load it occupies, that we need, how much we need to run service up to the roof to be able to run it. As you saw, we can tie that into our electrical lecture in terms of trying to figure out how many circuit breaker panels, what voltage we're running up to it, and be able to size all that. And then lastly, like we talked about in logistics, each of these units have a weight, and we have to find a way to pick them to the top of the building. So we need to have a crane that's capable of making the pick, making the reach, and being able to handle that weight. So it could determine whether you have something like a crawler crane that could reach from the street, or some form of a hydraulic crane, or do we need to really have a tower crane or building mounted crane to be able to make these picks? So it all kind of ties hand in hand. So knowing how to get to the size of the AC system determines a lot of other things in and around your building that are kind of intertwined, right? The electrical services as well as the weights of the equipment and the picks you have to make. So all things that have to be considered. Okay, so we'll continue on with this lecture. I'll end this section here. We'll likely have 2 more sections to complete online here. All right, thanks very much. All right, hi everybody. We're gonna start off this last online lecture, picking up where we left off in the HVAC lecture, the sections that we did not get because we were going over the midterm and stuff. So where we left it was this slide number 35, the commercial air-cooled AC system. And I had mentioned that this is critical because generally we also have a lot of HVAC considerations on the roof of a building, and basically deciding what kind of HVAC system you use will determine a lot. How much ductwork you need, the locations and reinforcements on the roof that you need to hold equipment, and then the number of lines that you need getting to and from each floor, and how that takes things out, whether it be water or air from the system that performs the cooling. So right here you see an air-cooled system. You see a number of fans in place, and basically what happens here is that air is used to cool the water. So basically a bunch of fans blowing on it to reduce the temperature, so that the blowers inside push that cold air from the water through the system, right? And that's what's coming through the ducts and out into the vents into the room. All right, but let's go through a couple of the different types of systems. There's both chilled water and chilled air ones. First is the AC chilled water. This uses a cooling tower that cools the water, or at least reduces the temperature of exhaust water, and sends it back through a chiller. Inside the chiller uses condensation to basically extract heat from the water in the second loop, which kind of then becomes cool enough to be passed through the system. A fan blows, fans and filters basically blow air through that cold water piping, and that's the cool air that comes out on the other side in through the vent. So make things a little clearer, this is the diagram. All right, so what's critical to see here, you have the cooling tower, which is usually on the roof of the building. All right, the exhaust water, as I call it, will be pushed up from the chiller up to the cooling tower so that the cooling tower can cool it off a bit. All right, and bring it down back into the chiller where it extracts some of the temperature from the water that's going through the cooling system. All right, in that second loop below, and hopefully you can see it with this arrow, cool air is passed through around 45 degrees through this internal piping. Air is passed through here, and it's the blower that's being controlled by the HVAC system and the thermal unit. If we want 65 degree air, this continues to blow through there until the temperature reaches 65 degrees wherever the end of this ductwork is, and then it shuts off. Okay, so what happens is when you're blowing air through this cool water, that air is ambient air that then becomes cool. So what happens is the air cools off, but the water absorbs that heat. All right, and the heat gets passed up through the chiller again. In the chiller, this outside water extracts heat from that return water from the blowers, and it cools it back down to the point where it can pass through this section here and continue maintaining cool air out of the ductwork. All right, so the second version we have is a condensed water system, and this uses what's called a direct expansion action to it. And the real difference between what we just saw and direct expansion is that it uses air to extract the heat versus water. Okay, so that for the most part, they're using air. All right. The evaporator is in direct contact with the air, and it's called the evaporator. It uses a refrigerant that passes through a valve to reduce the pressure and the temperature. All right. And this may be something that you're familiar with, which also uses a cooling tower. And these direct expansion units can be used on each floor. And what makes this, an improvement for a lot of the larger buildings that we build is that there can be less ductwork. Each floor kind of has its own equipment, so it's not like if something goes wrong, the entire system goes down. That direct expansion unit is used basically on a floor-by-floor basis. They can isolate it, repair it, get it working again, and it's only one floor out of 20 or 30 or however many are in your building that go down. So there's redundancy of equipment, and then it's a little easier to maintain things when you have that redundancy. All right, so again, just to reiterate, the cooling tower is used here as well, which uses the airflow instead of water. All right, and this looks like right here. This is what the cooling tower will look like. Very similar, but you see how you've got the return piping here, and basically it uses air to cool it. Big fans, blowers go off here, lots of vents and ducts to reduce that temperature, bring air in and take it out. So that's basically the two basic type of AC units. Either way you go, you're going to have equipment on the roof. You're going to have a lot of piping. You're going to have duct work, and really, it just depends on what kind of equipment and what the preference is. Some other ways that we try to cool buildings include, in terms of trying to get lead points, include ice storage. Basically, you have these massive cooling tanks below grade, kept as cool as possible, and that's your source for the cool air. Water would pass through there, air could pass through there, depending on what kind of system you have. And it's an attempt to reduce the amount of electrical load by having these ice storage tanks down there. And it does help reduce that load in terms of using energy to create the cool air when we can use it. All right, and there's other systems like cogeneration systems, which you don't have to know too much about, and the geothermal process, where you're using actually cool temperatures from the ground around you. From tunneling in New York City, basically, the air temperature below ground is usually about 55 to 60 degrees, just below ground, so it's pretty constant. So if you can tap into that, and that's cool enough to serve the purposes of cooling your building, then by tapping into that cooler air below ground and pumping that up into the warmer airspace, it can be pretty effective. All right, so what becomes, after the system is selected and all that is calculated out and everything is sized, all right, we'll go through all our calculations for our solar load and heat load and people load, electrical load, anything that generates heat in the building, and we're trying to, we have that all figured out. We know the type of equipment we're using, how big it is, how much it weighs, where it's going to go. Really, at that point, it's more about operating the system and getting it to function to where it's efficient and cooling off everywhere it needs to cool off. So really in this airflow diagram, I want to point out that there are two ways, or two means of doing that. Um, and really, whatever system you pick, there's two ways of modulating the temperature. It's either through variable air volumes or variable temperatures. Okay, so there's within the system, there's two ways of doing this. VAV, or variable air volume systems, means that we're modulating the amount of air passing through the space to change the temperature. And the temperature that's coming through the ducts, or the temperature of the air coming through the ducts, is constant. So basically, if you want to reduce your temperature greater, you would have a higher airflow coming through the duct. So your system would open up the ducts so that it's pouring in a lot of air. As it gets closer to the desired temperature and cooling off the room, and the thermostat gets close to your target temperature, it will start reducing the amount of air coming through to the point that it's in a maintenance mode, where just enough air is coming through to maintain that selected temperature. All right, so the volume of the air is what changes coming through. The second version of this system, it's the same volume of air, so it's not variable, it's constant, but the system actually changes the temperature, depending on, the source, wherever the air is blowing in from. It'll increase the amount of cool water or refrigerant or whatever it is that's cooling your air that's coming through the ducts. It'll increase that output so that the air is cooler coming out of the ducts, and it'll come at the same volume at all times. So there won't be louvers, there won't be vents that can change, openings from small to large to change that airflow. It'll be a constant airflow, and the temperature within the duct will change. But most typical is the VAV, because it's easier to maintain a temperature. As you saw through those systems, it's typically one temperature that's coming through. As we saw, 45 degrees coming through the water piping there, that the air is passing over. So it's pretty easy to vary the airflow over that constant temperature. All right, so you'll see this quite often, VAVs. Right, so pretty critical in terms of air conditioning systems. All right, so one of the measurements or units of measurement we use in a VAV is the cubic feet per minute. Right? And that's basically just a way to measure the volume of air going through the duct. All right, and this is also related to BTUs. Right, so if you know how many BTU you have, or you know how many cubic feet per minute, you can arrange this and the temperature of the room that you're trying to cool, plus the temperature of the air in the ducts. You can basically figure out how many cubic foot per minute you need to obtain those temperatures. Okay, so in this given case, the temperature of a room, the temperature of the duct, you should be able to figure out how many CFM or how many BTU it takes to get to a certain CFM. All right, so within these air units, the way we vary the air is we have what's called a damper. So that's basically what's inside the variable air volume controls that limits the airflow or opens up fully to give maximum airflow to come through. There's a control unit, as you see, that controls that mechanical damper. All right, so looking at a floor plan, basically, we like to have our air handling units to be efficient to come up through the center of the building, so that way it's an even dispersion through the pipe, through the ductwork, right, to each of the VAVs. And basically, as you see, when you start the run closest to the AHU, that likely will have the smallest opening to get air through because it's at its coolest. All right, so if that, say we're using 50-degree air, as the air passes through the building out to wherever that farthest duct is, it's likely that it's a little bit warmer, right? Because it's passed through warmer areas, it's passed through warm rooms, it's gone through ducts. So even if it's insulated, it's doing its job by cooling the air, and it actually gets, I mean, by cooling the rooms and the air within those ducts get a little warmer. So you would expect those openings in the control unit, those dampers, to be a little more wide open, letting more air in because it's not as cool as the air at the beginning of the run. Right, so this is a typical building airflow in a nice diagram. You got that condensed water coming in from the cooling tower through the AC unit. Right, so now it's going through the ceiling, through all the duct work. Right, the thermostat controls the feedback that goes to the unit, which dictates the opening in the VAV box. Right, all of this is up in the plenum space, which is the area that's above the ceiling. So it's generally it's usually hidden from sight, and all you'll see are the vents. Right, you see some more modern architecture, and in settings where they don't really care what you see above them. You see this in a lot of chain restaurants now, where they'll have the exposed piping. They don't necessarily put a ceiling in. Saves them costs in construction, and no one. You're there just to buy food. You don't care what the aesthetics are like above you. All right. So again, the VAV depends on temperature settings. It will often have a secondary blower. In the long run, if the air from the air handling units has to travel a long way and it loses some of its velocity, so to keep air moving through the vents, there might be another blower along that run just to keep things moving along. Right, so the typical thermostat, very old-fashioned one. You set your desired temperature, or you can set an on and off. On it when it hits 70, off when it hits 65, that kind of thing. All right, so it's very important in terms of trying to figure out the layout of the ductwork, and ductwork itself becomes a very significant mechanical trades issue during construction. As you can see from this kind of 3D model, all right, we're fighting for space in the plenum. All right, so below the gray, which is the floor structure, above the floor below, and then you see directly below that you have tons of piping. All right, tons of ductwork. There could be electrical conduit in there. All right, so you see all the different systems, yellow, blue, and red, which is air conditioning, heating, and plumbing, all kind of fighting for the same area. All right, so it's a difficult task for those managing the construction to kind of figure out where everything's going and to develop detailed drawings so that these can be installed without any kind of interferences with one another. Right, and one last drive I want to talk about. We talked about the variable air, and then we had the constant air. There's also variable speed drives, which can increase the speed at which the air carries through the ductwork. Not necessarily anything we need to know, but just know that there are options and other ways of doing things. Right, now ductwork becomes very critical in terms of not only how you lay things out, knowing where things belong, and then designing the ductwork and installing the ductwork so that it's cost efficient for the trades. Right, so in fabrication, there's engineering drawings. Those have to be turned into detailed shop drawings that get submitted back to the engineer to see that it meets the requirements, that the size of the ducts are good, that the runs of the ducts are good, there are not too many turns in it. And once the engineer approves it, it gets sent back, approved as noted or approved, and fabrication can start. Excuse me. So critical with the ductwork is finding a way to hang it, right? And then to also make sure that it meets all of the fire code requirements. On most ductwork, there'll be some form of insulation so that you don't lose the temperature, or you don't quickly lose the temperature along the run of the duct. All right, so if it's a 50-degree, air that's coming out 5 feet away from where you pass through the cool water, you don't want that temperature to be 52, 53, 54, and onwards going up. So we have to maintain the speed of the air. We have to maintain an insulated duct so that we can control those temperatures within it and not lose too much of that cool air. All right, so this is kind of a key sheet to the exercises. You can expand this a little bit to see it better. But basically, depending on the gauge of the metal we use, there's different weights, all right, pounds per square foot. So we need to know how much square foot of duct we're using at all times. All right, so when you look at ductwork, this is what the ductwork will look like, whether it's exposed or up in the plenum area above the ceiling. All right, as the tin knockers install it, this is basically what it will look like. All right, so each of these are sized specifically per the shop drawing and installed and hung where they need to be. All right, when we talk about, we talk about insulation. This is what typical duct insulation looks like. It's usually wrapped in some kind of insulating material with a reflective foil on the outside to maintain the temperatures within the duct. All right, so what we do when we're looking at ducts is what the most efficient sizing would be. And typically, the less surface area you can have of the duct, the better, because it gives you less opportunity to lose temperature to the outside and surroundings. All right, so the smaller the perimeter, the better. It also generally leads to a lighter duct, which is easier to install. All right, so those are the most important considerations when it comes to the ductwork. So if we can fit a particular shape that reduces the perimeter of the duct, it's going to cost us less, and it's also going to be easier in terms of the amount of weight that we need to lift and support. So all around, it's a cheaper alternative. And it all depends on generally the shape. So you can see here round versus rectangular, right? Both of them in terms of area can provide the same amount of air, 203 versus 200 inches square. All right, very negligible in difference, practically the same. Okay, but the perimeter of the rectangular one is much greater than the perimeter of the circular one. All right, so in this case, the circular one would be a more efficient duct, carries the same amount of air, and would be lighter, and when insulated would have the ability to maintain its temperature a little bit better because it has less exposed surface to that warm air on the outside. But as you can see here, 16 inches of depth to make that circle versus 7 inches of depth to make that rectangle. So if your plenum doesn't have 16 inches available to it, plus a couple of inches to hang, to put up the struts and hangers and all the things that are needed to connect the ductwork, then you won't be able to use it. So the most efficient shape isn't always the one that can fit in the space, right? But if space isn't a constraint, then obviously here in this example, using the round duct would be preferred. Okay. So here's we have an example in the homework. and this is basically a trial problem that we'll go through. All right, so you can see here there's different duct sizes. All right, it gives you a square duct here, 12 by 12, and 10-foot run. It has a 14 by 12 rectangular one for a 12-foot run here, 24 by 18 inch rectangular duct for, let's see, how long is that? That's a 32-foot run, and then a 15-foot run of 12 by 10 rectangular. Right, and the idea is to determine the weights of these ducts. And we can use this following chart, all right, which gives us a very good approximation. Now, what I have to point out to you in true, I guess, detailing, we don't just take each of the straight runs, add them up, and put them together. All right, we have to take considerations for where there are elbows, which are those turns, okay, where this duct hits this duct and connects. All right, that's considered an elbow. We need a little more extra duct work than just the 12-foot and the 20-foot to make that connection and turn happen. So we actually have to add a little bit of weight for that. And we basically take a generalized couple of feet of additional. Also, when we're installing and we're thinking of estimating for this ductwork, we usually have to estimate that there's going to be what we call waste. All right, so additional duct has to be ordered so that things could be hung properly. If there's a miscut in the field, we have enough ductwork to continue doing our work without having to wait for another shipment or order. All right, so particularly in this trade, we need to estimate about 20% additional duct upon order to be able to do a final installation. Particularly if it's aluminum or copper or softer metal that could get damaged more easily than steel. If we're using steel, we can use 10 to 15% as the estimated waste in terms of finishing up that ductwork. Right, but anyway, this is a key graph to learn. All right, so the duct is in perimeter and inches, and again, perimeter. All right, as we go back to our example, all right, with this rectangular, all right, the perimeter here is 72 inches, meaning 29 plus 29, all right, for the long sides, plus 7 plus 7. All right, so that gives you 58 plus 14 equals 72 inches. All right, and this example here, we've got a 12 by 12. All right, so that means 4 sides of 12, your perimeter is 48 inches. All right, a 12 by 10 duct would have 2 sides of 12 plus 2 sides of 10, which equals 44 inches. All right, so that's your perimeter in inches of the duct. Then whatever material you're given, whether it's 20 gauge steel or 22 gauge steel, whatever it is, all right, you go over to that number. Say we had 72 before for that rectangular duct. All right, so for every foot of that duct, if it was 20 gauge steel, all right, we're talking about estimated about 7 pounds. If it was the lighter gauge, that 22 gauge steel, we're over a little bit more like 6 pounds per foot. All right, so it gives you an idea of how much each of those runs weigh, so you can figure out how to install it, what kind of equipment you need or manpower you need to put it into place. All right, and so not only does it give you an idea of the weight, it also gives you an idea of the pricing. All right, so again, pricing is done by weight. Usually the heavier gauge stuff is more expensive, and then that's how we can estimate out the ductwork. So when you think about a building, right, you have a couple of units that the cooling tower, or whatever the condenser unit is, your DX units, whatever might be in place. There's a few of them, right? But the thing that carries the most weight, the most tradesperson's time, is installing all of this ductwork. So the ductwork becomes actually a very significant part of the system in terms of trying to figure out the weight, and that's why it's very important to do so. All right, and I'll end this portion of the lecture here. We'll pick up with air balancing on the next half. So there'll be 2 HVAC portions of this lecture, and then there'll be the plumbing half. and that'll be the end of the last online lecture. All right, thanks. All right, hi everybody. We're gonna start off this last online lecture. All right, and just to finish up the in-class lecture, or finish up the lecture on HVAC, we'll pick up where we left off with air balancing. Right, and this is the act of checking the actual air that's coming through your vents from your HVAC system against the design criteria, or to see that you're getting what you expect to get when you install the system. And of course, if there's differences in what you're getting versus what you expect to get, then you have to make some kind of adjustments to the system to make sure you're getting that airflow that you need in cubic feet per minute. This is also the time, just prior to turnover of a system A, where you're confirming that you're meeting the specification requirements, and then probably the owner or the eventual user can also make adjustments to their comfort. If you install it as per the design, it's at the temperature and the airflow that's required, and they feel it's a little stuffy or it might be too cold for their taste, then that's the time where you can make an adjustment prior to final handover, and then it's up to them to maintain it after that point. So the way we do that are basically through what we call a diffuser and hood, and this is a way of just testing what's coming through the vent. So you put that diffuser up against the vent area on the ceiling where the air is flowing out of, and there's a meter below it, just below where the man is holding the handle there to keep it up. There's a readout that can be recorded that says basically how many CFM you're getting out of that particular vent, and you test all the vents to make sure that they're coming out whatever volume they're supposed to come out, and making sure that not big losses along the line where you're further from the fans or the VAVs, that you're getting different readings or lower readings than you should. Alright, so that's what the equipment looks like. There's a little monitor on the bottom there that the readout will give you, and it folds up, packs away nicely, and basically every HVAC installer has one of these and can check to ensure that they've met the requirements of the spec. They usually fill out a sheet similar to this that shows what the design load in each of the vents is supposed to be, what they record in their final balancing report after they've made all of their adjustments, and turn it over and say, here's what we have at the time of turnover and acceptance. And if 6 months from now you get something different, then you need to make adjustments as you need to get back to this level. As we talked about in class, there's a couple of different ways to distribute air, and we talked about there being vents in the ceiling or vents on the floor, and how typically warm air will rise and occupy the space at the closer to the top of the ceiling versus colder air that will usually sink and be towards the bottom. You'll have generally a couple degrees differential between the floor air temperature and the ceiling air temperature. And we talked about how it might be easier to heat a room with vents from the bottom, and AC might do better from vents from the top. Simply because the cold air has a nature to hit the warm air and then make its way towards the ground, while the heat will rise up through the room and keep that airspace warm as it continues to rise. So, but we all know that typically you're not going to stick vents and systems in both the ceiling and the floor, just out of logistics of where everything can go, and be out of budget, and that you don't really need two ducts and two vent systems to do that work. So you really only pick one or the other, depending on where you are in the climate and whether you expect to use air conditioning or heating more may determine whether you design or your design will call for installation in the ceiling or the floor. All right, so there could be the underfloor, and of course up to the ceiling as well. All right, so there's obviously ventilation requirements. You have to maintain oxygen levels. You have to maintain airflow. You don't want to have stale air in any of your air spaces, particularly if it's a living space or workspace, since so many hours are spent there. So really the point of ventilation is to exchange the air within that area. Make sure that you have the right levels of oxygen, that you're removing any of the odors or chemicals that may be in the air, that come from carpeting. We all have heard VOC, volatile organic compounds. Those are what basically create the odors, and with those odors come chemical levels in things like paint, carpeting, finishing for the floors or windows. Any of those chemicals may have a VOC level, and if you're doing green building, you'll have a very low VOC level, or using materials that have no VOC. So then you don't have so much of an issue of those things polluting your air, but you still need to exchange the ventilation, remove carbon dioxide, and replace with oxygen. All right, so in other considerations with your HVAC system, it's not just simply an exercise in making sure that it doesn't fall down when it's installed, that it's hung properly, but these things have to be installed in a way such that you don't hear so much noise coming from the system. Like you don't have rattling against your the Kindorf, rattling against the hangers that your vents or ducts are creating. So we have isolation hangers, we have padding that goes between that, and we also have to make sure that it's designed such that those duct runs aren't being overburdened by the flow that's going through them to the point that they're vibrating or rattling. So all that's taken into consideration when your HVAC system is designed and then installed. Condensation is also something we worry about with an HVAC system. Obviously, where there's temperature differences, like when you're on a very cold bus or train or subway, during the summer months. It's like the difference between being in a refrigerator and then stepping outside. It's 90 degrees. You get that condensation on the windows, and the same when it's 20 degrees outside and your house is nice and warm, and it's 70 degrees on the inside. You see that buildup of condensate. The same thing happens in the building system. It may not be as evident, but within that HVAC system, within the ductwork, there can be a buildup of water, and basically you have to accommodate for that. You have drip lines, drain lines in there. Your ductwork will probably have a very minuscule angle to it, so that any condensate or water buildup in it can drain towards one of these. And then there's also pans that fill up with alarm levels if there's excessive amount of condensate, where either a pump will kick in or you go and drain the bucket or the pan and then make sure it's dry and replace it. All right, so all of that is usually inspected upon maintenance, especially in a ventilation system. Something like condensate can be damaging, and that it could lead to the start of mold or other things that you don't want in your air. That's why you replace the filters often and make sure that you have a way to deal with moisture buildup. Okay, another thing we talk about are isolators. These are basically to deal with any seismic load, shifts in the building, movements, rocking back and forth from things like wind in your structure, so that the equipment itself, isn't fixed and doesn't undergo the stresses that the steel structure goes through, to make sure that it continues to operate properly and that it's in alignment with what it needs. Because obviously, if you start coming out of alignment, you may not have the same airflow through your ducts, through your equipment, and that might start impacting how well it operates. All right, so just another version there of how major equipment may have those isolation dampers on the bases or pedestals. Okay. Just a review kind of calculation here. If you have, obviously when you have lighting, there's going to be an impact on the heat within the building. And we talk about the heat transfer and what that load does for it. So if you reduce the impact or the wattage that you're using by shifting to new bulbs, smaller bulbs maybe, lower lights, or even more efficient lighting, there's going to be a significant difference in the amount of air conditioning you'll need to cool those floors in the summer. So it's just something to keep in mind. Here's a sample calculation similar to what you'll see on the homework. So study this and just make sure you understand where the numbers are coming from. It's just basically the difference in watts times the square foot times the factor that 3.41 watts equals a BTU. So that's how you get to 85,000, as we covered in the first part of the lecture. You take that 85,000 BTU divided by 12,000, which is how you convert to tons, and that's 7 tons per floor of cooling that you save. So you're saving on the electricity and the wear and tear on the equipment, and that's only isolating just a lighting example. All right, so there are tons of different heating systems as well. We all know that to generate heat you can use hot water, electric, air warming through hot coils, solar cells, geothermal heat exchangers. We've talked about cogen a couple of times between the electrical and the HVAC. So really, the most typical are electric heat, or oil heat, gas heat, which basically heats up the water, and you can use steam heat or electric heat. Alright, so typically a water boiler acts like this. You get combustion chamber, and it's fed by some kind of flammable material, either whether it's gas or oil. It warms the cool water that's coming in through the inlet, creates a hot water that builds up within the pipes, and then that water is now used either as hot water or for baseboard heating, and then the excess steam gets carried out through an exhaust. Alright, so that's what a giant boiler would look like for a large apartment complex or multi-story building. Geothermal is something we've kind of covered a couple of times, emphasizing the fact that many buildings have LEED requirements now. In fact, in the New York area, any federal or state building is required to obtain some form of LEED certification as part of the new construction. Okay, so the government has stepped in and figured they got to get on board with LEED requirements. All right, so geothermal heating and cooling, again, is tapping into the temperatures within the earth to kind of assist in the heating and cooling. It may not be the entire system, but it could be used in portions of the building. because remember, a few hundred feet below the Earth, you're usually at a pretty stable 55, 50 degrees. So that could either be used to pump in warmer air than you have, depending on the climate, or cooler air for air conditioning. So, some tips in terms of energy savings when you have discussions with your developers and your architects and engineers, and you want to create a very inhabitable, livable, and marketable place nowadays. You want to show energy savings and Energy Star criteria. So take a look at your HVAC design, see what you can do with them as far as increasing ways you can save energy, using higher diversity factors when you don't expect full occupancy at all times. Make sure you're meeting all the new state and federal energy codes. Sometimes we use thermal imaging as an aid to see where we're at with an existing condition. I'm going to go through a few slides of that. And as we saw in that quick calculation, just a simple reduction of lighting load or use of more efficient bulbs can make a big difference in the amount of energy that you're using to heat or cool. Knowing what facade material you're using, the types of windows, what kind of U values they have is a big deal. That could have a major effect on the amount of thermal load. Building orientation, we talked about which direction you want your entrances facing and how that plays into what makes something more marketable. And then obviously now that we're in the modern age, having building systems that are computer controlled and can read active conditions and adjust so that it's not programmed only to one temperature or one situation. And using a BMS is definitely something that should be considered. And this is just a typical standard value of what the heatings and control will be set to within a building system. When it's below a certain temperature, you'd like a minimum of 68 degrees, maximum of 78 within the interior. That's actually pretty high. Generally you see 72 set as like the top, 68, 65 as the heating element. So depending on what you want as those comfort levels, it will change how your system operates. So here's an example of that thermal imaging. Thermal imaging is used to often figure out where you're getting heat losses in a building, if there's any issues with the facade, where you might have poor seals within the facade. Blue is generally cooler and red is generally hotter. All right, so as you're going through, you can see the outline of what's a window. You can see where heat is generated, through heat pumps or convection. So you probably have a heater line along that wall there. And again, something like a light fixture, the bulb itself will be radiating heat, while the fixture around it will be fairly cool. All right, so there was a recent study a couple of years back where buildings around the city were thermally scanned, and the one that had the biggest issue was 675 3rd Avenue at the time. And when you look at it, you see the thermal image. It's basically glowing red, meaning that the temperature, it was 43 degrees on the exterior. All right, and you would expect that the exterior portion of the building would be somewhere close to that temperature, but heat is basically escaping on all sides of that building from the interior. So you can just think about what that's doing to the HVAC system, what it's doing to your boilers and your heaters. They're probably constantly running to maintain the temperatures within that floor, and the air is escaping all throughout that building. So not energy efficient and probably very costly to maintain and upkeep the heat. All right, so just some general guidelines. New equipment will lose about 16% of their efficiency within 1 year, and that's generally due to poor maintenance or not upkeeping it. All right, when something's nice and shiny and new and perfect, it's going to operate well. As soon as you let it go a few months and there's buildup of dirt, debris, water, and you're not taking proper care of it, not changing out filters as frequently as they should be, you will start losing efficiency and it'll start running down. And it's one of the major costs of your building, and something that has a shorter lifespan than the structure itself. So the longer you can keep it in good shape, the less maintenance, the less cost there is towards excessive maintenance and or replacement. So you want to make sure that you have a good maintenance crew on hand, that they're following all the manufacturer's recommendations, and that they're able to identify when something isn't operating properly. If not to keep things silent, if you find that you're replacing a filter every few months because it's overloaded with something, then there's an issue. If really you're replacing something far more often than it should be, you have to start being able to identify the signs that could indicate a problem that could be taken care of early rather than letting it keep going on and then leading to a total replacement of a part or a system. All right, so having a BMS system in place is one way to help ensure that something's operating efficiency, that it's computer controlled, that there can be alarms set for when something isn't working exactly right, and you can take care of it immediately rather than just finding it a few weeks later in general maintenance. Right, and really how that works, it's really just a computerized system where all the inputs are there, and as soon as there ends up being, you set your limits as to what could indicate issues. If you feel that the water flow is lower than it needs to be, it'll notice that. If you certain levels are too high, if there's too much feedback in electrical, there'll be a number of different things that could signal the BMS to show that there could be an issue. Alright, so there you go. That's heating, ventilation, and air conditioning. We have a homework. Alright, and make sure you use this homework slide. I'm going to post it. Okay, the reason we didn't get to this in the last portion of the lecture, and it wasn't due a week ago, so I've edited this to make it a lot more clear. So this is due next week, okay, at class time or before class time, right? And basically it's pretty clear. I gave you the dimensions of a floor. You have the orientation. All right, there was a slide earlier in the lecture that talked about what the heat transmission is like, depending on the orientation of the building and the time of day and the orientation in terms of what parallel it is or latitude it is. All right, so in this particular case, you have a 10,000 square foot floor. All right, 100 foot, basically it's a square, 100 foot on each side. And it uses double quarter-inch with airspace cleared glass at 10-foot heights around the entire perimeter of the floor. And it's oriented so that the entrance is on the north, so you have a north, east, south, and west face. And what I'd like you to do is give me two answers. Number one, what's the total solar load in BTUs, given the condition that it's July 23rd at 40 degrees north latitude at two different times of day? And for each of those times of day, I'd like you to give me what the total tons of air conditioning required is based on those loads and these factors. So the factors are, there's 100 people working on that floor. You're using fluorescent lighting loads of about 2 watts per square foot for that entire floor. And that there's a 20-degree difference between the temperature you're maintaining on the inside, which is 75 degrees, and 95 degrees, which is outside. And just to make things simpler, we're going to use that 20-degree difference both at 8 a.m. and 11 a.m. Okay? So that's what you have to give me. Don't take into any consideration for diversity. Just give me the full answer at 100%. And also note that this floor is just one of the many floors in the building. It's not the one just directly below the roof. Because obviously if we were doing the one that's directly below the roof, we have to consider the roof as a fifth surface. Okay, so it's not just 4 different sides. It would be the roof would have some coefficient based on the type of roofing you're using, and would also have that difference in temperature, and we'd have to figure out what the heat loss or gain is through that as well. But for this example, let's just consider the 4 sides of the building on this floor. Okay, so hope that's clear. One calculation I'd like to just run through with you here for temperatures and BTUs. If you're trying to find a BTU for heat transmission through the glass, through the material, it's basically the temperature difference between the outside and the inside. times the surface area that you have that temperature differential. And I should say temperature differential, the first two words there, but temperature differential, the difference in temperature between outside and inside, times the surface area you're trying to calculate it for, times whatever the coefficient of the material is. And the following slides have the charts for the coefficients of materials of the various glasses and windows and spacings. So you just pluck that number off that chart. All right, so that should help you out during the homework. Here are the two charts that it comes with, and any additional chart information you'll find earlier in the lecture on a couple of different slides. So that's what I'm looking for as the calculation homework for the HVAC. So this will be due next week when we meet in person. All right, thanks very much, and hope you enjoyed the catch-up to finish up HVAC.